Curious to see if this is going to show up as just my... Which camera is it going to be? Of course. That's useless. Oh well. Anybody watching the stream today is just going to see this. So, David and Luke and people here, see if you can figure out first the velocity that this car would need to have to not lose contact with the road. It's a 1,000-kilogram car. It enters this loop-the-loop, this perfect circle, and assume that it's traveling at uniform speed the whole time. So the speed of the car is exactly the same throughout the whole thing. The radius of the loop is 5 meters, and the question is, the first question is, how fast does it need to be going so that when it gets to the top, it's just barely touching the road? So another way of stating this is, if you're the car, or if you were standing here, you'd feel the road pushing into you. You'd feel your feet pushing into the road. You'd feel that as you went up here, that you'd sort of be slinging yourself outward, but the road would be pushing you back in. But that feeling would get weaker and weaker and weaker and weaker until it's just on the edge of being gone right there. So the question is, how fast does the car need to go for that to happen? If you went any slower, the car would just disconnect from the top and fall off. Went any faster, it'd be totally fine. So try that, and I'm going to circulate around and check people's answers. And if you're at home, you can put it in the chat, and I'll tell you if it's right, if I'm here to look at it. And I'm going to go get some paper so I can work on paper. Oh, come
on. We can't see the question now.
Oh, okay.
We can see your paper.
You can see my paper, yeah. So it's basically, this is the question. I'm just rewriting it. The velocity you're trying to figure out, the radius is 5 meters. So what's is that? I'll be back in a moment, wandering around the room. So once you get V, which we'll talk about in just a minute, the next goal is for each of these cars to draw arrows representing the individual force vectors, and name the forces and also give a magnitude. So for example, I'll do one of them for you. One of the forces acting on this car is its weight, and the weight is mass times gravity. So 1,000 times 9.8, it's going to be, or mass times g, 9,800 newtons. So there's one of them, but there are a bunch of other forces on these other cars. The top one is probably going to be the easiest. The bottom one's the second easiest. These two on the side are not hard, but they're tricky. They're so tricky that hardly anybody ever gets them. had something. Yes, David, that's right. Correct. Does anybody want a little bit more time to work on the velocity before I show you how to do it?
Yep.
Yeah? Okay. We'll give you a little longer. Hey, Sid.
Hi.
So, Sid, get some paper out, and we're working on this problem. The first part is if there's a car that is going around a loop-the-loop that has a 5-meter radius, and it's going just barely fast enough so that it doesn't disconnect from the ceiling at the top. First, how fast is it going? And then second, what are the forces acting on it, and how strong are they when it's here, here, and here? Riam, are you getting close? Should I go ahead?
Yes.
Okay. So I'm going to do the velocity part. This is the important place for figuring out this velocity, because if it's going to come loose, this is where it's going to happen. And I guess you could really analyze each of these places and come up with different velocities, and but eventually you would come to the conclusion that this is the important place. So to do this, I'm just going to approach it like I do all these the other problems in the last couple of units, which is to draw the forces acting on it and then write equations for net force 2 different ways. So the weight, I'm going to go ahead and do that for all these cars. The weight is 9,800 newtons in every situation. That's not going to change. Although, if you wanted to be a smarty pants, you could say that the weight is actually different. The weight's only the same at which 2 of these places. If you really wanted to split hairs. No. So Claire, where would it be the same?
The very top and the very bottom.
No. That's what some people said in here.
The right and to the left.
Right and the left. Why, David?
Because there's no normal force. Is that what? Or no?
No.
Is it? I don't know. But
That's what. Yeah, it's a. Luke, why would it just be these?
Because at that point they are the same distance from the center of the Earth.
Right. So 2 ways to calculate weight. One is to use mg. G is just, it's 9.8 approximately, and that's something we've arrived at that works at the surface of the Earth. But the other way to do it is to do this. And it's dependent on the distance from the center of the Earth. So this is closer to the center of the Earth, so gravity should be stronger here, and it should weigh a little bit less. As you get farther and farther out, if you go out into space, you're virtually weightless if you go far enough. So if you're a real smarty pants, these are the same. This is a little bit lighter than 9,800. This is a little bit heavier, but good enough. So they're all 9,800. But back to this. Are there any other forces acting on this car? In reality, if the car were going around here at a constant rate and it's going just fast enough to not fall off the ceiling, can you think of any other force that would be acting on it? What's that, David?
the centripetal force.
So the centripetal force is acting on it. I'm glad you brought that up. But the centripetal force is just another name for net force in any uniform circular motion. So this if I'm analyzing the top and I write the net force at the top, I would just say it's negative mv squared over r, because the mv squared over r is the centripetal force. That's the force toward the center acting on any object that has this mass that's moving at constant speed. But that's the net force. So that's not an individual force like weight. That's what we're going to get if we add weight to all the other individual forces, then we're going to get this. So is there another individual force?
There's no other individual forces in there.
No, although in real life, what other force would there be? There'd be some kind of air resistance and probably friction of some rubbing in there, but let's just assume for this that we don't include air resistance. So really, this is going to be the only one. For some of these other cars, like the one sitting down at the bottom, there's going to be a normal force because the ground is pushing up. But the whole premise of this question is when you get to the top, the car is no longer actually really pressing against the top, and the top's not pressing against it. So this is it. So that's it. Now, instead of writing, I'm just doing what I always do, which is I write net force as, this is like the old F equals ma, and then this is the sum of the forces, except it's not ma anymore because ma isn't as useful when we're doing a uniform circle. I'm plugging in a as v squared over r. So that's the F equals ma part, and then I add up all the forces. Instead of writing negative 9,800, I guess I can write that, 9,800 newtons. I'm just going to write that as mg, negative mg, because that's ultimately going to be easier for me here. You'll see why. So first, this is negative because the weight's pulling down. This is negative because the center is below it, so the centripetal force is down. So I can just write this equals this. So I have negative mv squared over r equals negative mg, and I can cancel out the m, so that's why it's easier than doing this. So I just get g equals v squared over r. V squared over r in this case is 5 equals 9.8 meters per second squared. So if I multiply 9.8 times 5, I get 49, and then the square root of 49 is 7. So that's the speed of this car. V equals 7 meters per second. And this picture's done. There's really only one force acting on the car there. It's a 9,800 Newton weight pushing toward the center. That equals the centripetal force. So now try this one next, and after you've done this one, try this one. So this is the next harder one, and then these two are I would say the trickiest to get right. Draw every force that's acting on the car here, show its direction, give it a name, and then calculate what it is. And I'll circulate around. If you're one of the people who's remote right now, just raise your hand, and then I'll come and just hold it up to the screen, and I'll tell you if it's right. This was hard for the other class. These are tricky. The bottom one you ought to be able to do. The side ones are very tricky.
Wait, what are we trying to solve for the bottom?
Just draw all the individual forces that are acting on this car. I've drawn one. The weight of it is 9,800 newtons downward. So draw every other individual force. You don't have to draw the net force. If you're in here and you think you have it, just raise your hand and I'll come and check it. You're trying to find all the other forces that are acting on this car. Just drawing them, labeling it. Like this one, I've called it the weight, and it's 9,800 newtons. So if you draw another arrow, label it with a good name, a name that makes sense, and then how many newtons of force. And make sure it's in the right direction. Don't worry about the length of the arrow. Ooh. So David, you can put it down. I have a look at it. So if I add up those two forces that I see there, I get 0. And it should have a net force that's not 0. In fact, everywhere in this circle, the net force should have the same absolute value.
No, I know what I did wrong.
Okay.
Can we ask you a question?
Yeah, go ahead. This is all just about learning. Do you have a question, or did you just want to know if you could ask questions? Hypothetically.
I do have a question. I just don't know if I want to say it out loud.
You can do that, sure. Or you can put it in the chat. I'll take it either way. I don't really care.
I mean, I put it in the chat already. So.
Oh, you did? Okay. Yes, David. So, yes, Claire. Yes. Always there is. Sorry.
Yeah, I solved for the net force. I just subtracted instead of adding.
Got it.
So, for the...
Has anybody in here got it? The other forces? So on my piece of paper, I just wrote the word constant, pointing over at this this so-called V here, 7 meters per second. So there are a couple of things to parse out from my statement there. I said it's the so-called V, and I wrote constant. So why am I calling it the so-called V, not the actual V? We calculated 7 meters per second. What I'm saying is that's not really the velocity.
Isn't that the speed?
That's the speed, exactly. So it's got a constant speed, but not a constant velocity. And Claire's question, just if nobody's seen it, was, is there acceleration? And the answer is yes. There's constant acceleration the whole time. So the speed is staying the same, but there's constant acceleration, and that's because there's constant changing of direction, which has to do with the way the acceleration's always in a different direction than the car is actually moving.
In this case, like since it's going in a circle,
Mhm.
how is the speed and velocity different?
So when the question, if people didn't hear it, was it's going in a circle, how are speed and velocity different? So right here, if I were to draw a velocity vector, it would be like this, and it would be 7 meters per second. But then when I get to the top, it would be like this, 7 meters per second. And then down here, it would be 7 meters per second. So if I were to describe the velocity, I would say 7 meters per second upward, 7 meters per second to the left, 7 meters per second downward. So it's always different velocity, but same speed. Does anybody want a little more time before I reveal the bottom one? Feel like it's been a pretty good amount of time. Probably should go ahead. All right, so the bottom one, I'm going to do exactly what I did with the top one. So this is what I did at the top. This is uniform circular motion. Therefore, the net force everywhere on the circle is going to be mv squared over r. The tricky thing is that mv squared over r is always directed toward the center. So when you're at the top, it's directed down. When you're at the bottom, it's directed up. So in a sense, it's different. So let me do net force at the bottom. And I'm going to write the same thing I wrote at the top, except I'm going to keep it positive because the net force is going to be directly upward toward the center, which is above. So it's mv squared over r. There's the net force. And then the other way to get the net force is to add up all the forces acting on the car. Now, if this were the only force, if I just stopped here, then the net force would be 9,800 newtons downward, and this car would be in free fall. It would be falling straight down. But there is another force that's preventing it from going down, and what's that? What's stopping it from just... The normal force, yeah, it's the road. The road's pushing straight back on it. So there's that. I don't know what the normal force is. If it were just the car sitting here, not going up, not going down, it would be, the normal force and the weight would be equal. But since the car's traveling in this weird curve, I can't say that. But what I can say is that that's it. There aren't any other forces. So if I add up the forces, I've got to add the normal force to the weight. This is up, this is down. So the net force is the normal force minus the weight. I'll say minus mg. And then maybe there's going to be some algebraic simplification I could do, or I could just write normal force minus 9,800. So this is the net force, this is the net force. Therefore, the normal force minus mg equals mv squared over r. And I think the easiest way to find the normal force at this point is to just plug in. I already know what the weight of this is. So this is normal force minus 9,800. And I've already calculated, actually no, I haven't calculated it, but I'm about to calculate mv squared over r. I kind of found it up at the top, but let me just go ahead and do that now. The mass is 1,000. V is 7. So, and then R is 5. So this would be 49 times 1,000, which is 49,000, divided by 5, which is, it ends up being, wait a second, what am I doing? 9,800. So mv squared over r, plugging in these numbers gives me 9,800. And the reason I was saying I found it up here is because up here, the net force at the top equaled the weight. So I knew the net force was 9,800. So I didn't really need to do all this. So down at the bottom, I get normal force minus 9,800 equals 9,800. So I just need to add 9,800 to both sides. Normal force equals 19,600. And so these two forces together give me the same net force that I have here. So when I'm done with this diagram, I can go to any of the cars, I can add up all the forces that I see there, and I should be left with 9,800 newtons pointed right at the center. Here there's just one. Here there's one going at the center that's twice as big as this one, so it comes out to 9,800 toward the center. All right, now I'll try this one. This is the really tricky one. It's mathematically easy, but conceptually difficult. If you've got the drawing, raise your hand. And if you're at home, do a little artificial hand. I'll see if it's right. And try to label the forces with their correct names. This would be a kind of a bonus-worthy question on a test. This isn't something I would. Don't think that because this is tricky, too tricky, that you're gonna not do well on the test. Still a good exercise, though. This is so much nicer than last class. Last class, the projector had already gone out at least twice by now. So again, if you've forgotten what we're doing, you're just trying to draw the remaining any other forces that are acting on this car on the right when it's climbing up the side of the circle. I will say this is unnatural. When cars go through loop-the-loops, and there's this guy that, if we have time, we'll watch him. There's this guy that runs in a loop-the-loop. They don't do it like this. So the assumptions for this are kind of unnatural. It's a bit of a hint. I've checked one answer, and that person was on the right track. I'll tell you, there are more than two forces. Here's a little bit of a hint, too. Does anybody want more time before I give more hints? I don't see any head shakes or nods. So maybe I'll just give you some hints then. The thing that is always, always, always true about something that's in circular motion is that the net force equals mv squared over r. So whatever and you also know the direction. So just this car that I've got my finger on, what's the direction of the net force? Up, down, left, or right? If it's going in a circle, it's always accelerating toward the center.
The center, so it'll be left.
Yeah, so the net force acting on this car, it's got to be toward the left. And it's got to be mv squared over r. So if you add up all the forces acting on it, we've got the sum of all those has to be a directly left force there. And the question is just what could those other forces be that would amount to that? You know, I just had an idea. Let's before we finish this, let's watch the guy run in a circle. The problem with this is when I try to show you this video, I may have to stop the recording.
I sent it to the listeners to look.
Yes, the answer is yes. So if this doesn't play, I'm just going to tell you what happens to this guy. Hopefully it'll play though, without being too jerky.
My name is Dane Walters, and I'm a stuntman who does tumbling, gymnastics and parkour. I'm attempting to run a loop. I've seen people do it on skateboard, I've seen people do it on BMX before. No one's ever tried it on their feet, so it's been nice to be the first guy to actually run it. It looked a lot bigger than what I thought it was going to be. Yeah, so it's not the easiest thing I've ever done. To be one of the first people to do things is always one of my ambitions. You know, I want to try and keep pushing the boundaries even further and further. See how far people can go.
Basically boils down to this centripetal force. You need to keep on accelerating. So you need to reach a certain speed. And I've worked out, it's quite good news actually, the speed at the top is 8.65 miles per hour. That's it.
Okay. 3, 2, 1, go. 17.
So he can run 17 miles per hour. He's got to be going 8.6 at the top. Seems like it would be easy, right? So why is he unable to run 8.6 at the top if he can run 17 miles per hour? Chris?
Isn't it gravity?
Yeah, what were you saying, Chris? Can what? So yeah, Riam, what do you mean by gravity? I think you're right, but expand on that a little bit.
Because it's like pulling him down, so he's trying to run and like gravity's keeping on pulling him down to the earth.
Right. So yeah, to go in the circle. Right. To go in the circle, as soon as you start running up a hill, especially if the hill's really steep, it's going to slow you down. But this this problem that I have here that I've given you is the assumption is, let me get back to this. The assumption is that the car is going to be going a constant speed the entire time. So if you're driving a car and you're maintaining constant speed, in the face of weight, which is pulling the car down, what do you have to do to keep your speed constant? If you're actually driving this car, what would you have to do to go up the wall? And
you have to push on the gas harder.
Yeah, you would have to push the accelerator. So, and there are a couple of ways to show that force here. I could either show the force of the car pushing straight up like this. I could say, this is the force of the car, which is probably the best way to do it. Or maybe I'll say this is the engine motor, whatever you want to say. I'll just call it the motor that's pushing the car up the hill. And but technically, if this were slippery, the motor wouldn't be able to do it. So what's technically pushing the car up the ramp? That wouldn't be pushing it up the ramp if the ramp were slippery. Friction. So really what's happening is that friction on this wall, the wall is pushing the car's tire up the hill. So it's an action and reaction thing. The tire pushes the wall down, the wall pushes the tire up, and in order to prevent the car from slowing down right now, what does the force of the motor have to be? Well, friction's allowing it to happen, but this is the problem here. The weight is pulling the car down. The motor is counteracting that weight. We want to have no change in
The motor
has to be what?
I was gonna say the motor has to be large. The force of the motor has to be bigger than the weight.
So if it is bigger,
maintain.
let's say that the motor force is stronger than that. Let's say the motor force is 10,000 and the weight is 9,800. Is the car going to move at a constant speed, or will it accelerate? It would accelerate, but that's not what it's doing. It's got to maintain constant speed in this. So the motor force needs to be 9,800. So as you drive up this wall right here, in order to not slow down, you have to counteract this force with an uphill force. It's got to be the same. Now the net force though, oh, I've already done this. The net force, so I divided this up into x and y dimension. The net force in the x dimension on the right, I'm going to just call negative mv squared over r. That's the centripetal force that's pulling it straight in. And the other way to describe that net force, this is only a description for net force. The other way to do it is to add up all the individual forces. So in the x dimension, there's really only one force. What's the name of this individual force? What's the thing that's actually pushing the car leftward?
Acceleration.
Acceleration isn't really a force. The normal force, yeah. So the normal force, the force of this wall is pushing it in. So as the car goes around, if these were your hands and you were holding a little creature in here that was running around in circles, you would feel the creature pushing against your hands. The faster it went, the harder it pushes against you. In fact, I've got a snowblower, and when the snow is shooting out of this chute like this, I can actually feel it kind of pushing the chute up. So you would feel as something goes around in here, when it gets to here, you'd feel the car pushing this way, and you'd have to push back. Otherwise, this whole circle would rupture. So the thing that's pushing the car in is the normal force. And the normal force is to the left. So this normal force has to equal mv squared over r, which we've already shown is 9,800. And then in the y dimension, well, the net force has to be straight left. So there can't be any force in the y dimension. So whatever forces I have in the y dimension have to cancel, because we know with uniform circular motion, the net force has to be left. So if we've got this force, we've got to have a canceling force, and that's the motor force. So now when the car is going down the hill here, on its way down, I've already got the weight. Somebody tell me another force that I should draw on that. Normal force going which way? To the right. And what will the value of that be? 9,800. And what's the third force? Yes, yeah, you'd have to brake. Otherwise, you'd speed up on the way down. So on the way up, to maintain constant speed, you've got to accelerate. Well, try to accelerate, but you won't. You've got to hit the gas. And then on the way down, you would speed up if you didn't hit the brakes. So I'm going to say it's brakes. And this would be 9,800 newtons. because it would have to balance out the weight pulling you down. Technically, again, it's friction. The brakes work by locking up the tires, and that means the tires push down on the wall and the wall pushes up on the tires, but I think brakes makes more sense. So it's kind of weird, really. If you look at this side and this side, they're totally symmetric. It just sort of seems like if we've got this extra force going up on this side, we ought to have an extra force going down on this side, but no. Got to have, on both sides, since weight is downward, we've got to balance that out. So this is really hard. I thought it would be worthwhile as an exercise, but don't expect anything that hard on the test. Let's watch the rest of the video.
Somebody show her that one back.
Well, this is it. And I've said that 3 times now, but this one is it. Well, I'm close, I reckon I'm close. Get close. You can't really go any further until you take the match out. Yeah, go for it.
Looks better in slow motion, actually. Make sure you drink Pepsi Max. Okay, so that's it for that. Let's see if I can find my way back to my website. All right, this thing down here, I think I've already deleted that. I had it in my mind we'd have a lot of extra time today, and we did this a couple of years ago, but I'm temporarily putting this on hold, probably not going to bring it back. It was just for everybody to look up some applications of circular motion, because there are a bunch of cool things related to centrifugal force and circular motion. Maybe we'll do it, but if we do it, it'll be later. But right now, I want to go over the homework, which was the test from last year. And I don't know if we'll have time for this 4-minute drill we didn't in the other class. I felt like I just fried their brains by that point. And if we have time, talk about what's on the test. But we've really got Monday to do that too. The test isn't until Tuesday, so we've got more time to prepare for it. All right. I want to show you at least one thing that there was a mistake on here. Somebody found one mistake yesterday. Was that, who pointed that out? Was that somebody in here? Anyway, there was a mistake. It was Jackson Tucker. So he found a problem yesterday that I fixed on here. And the problems arose from the fact that I had an answer key that I used when I was grading this test a long time ago. It was this, and I thought it was kind of messy, so I rewrote things. But when I rewrote them, I left some stuff out. So this came up last class. In number 7, I don't know if anybody did this and got the wrong answer and then was trying to follow my work, but my work didn't make any sense. And the reason it didn't make any sense was because if you solve this equation right over here, if you solve for r, you get 8.92 times 10 to the 6th meters, which is not the answer. But this is asking for the altitude. This is the orbital radius. So what I had to do, like if this is a planet, and you have the orbital radius, which is the center to some point out here, if you want the altitude of that, you have to subtract the radius of the planet. So this, solving for r here, will just give you this. You need to subtract that, which is the radius of the Earth, to get the actual answer. Are there any questions on here you want to talk about, or want me to talk about? Yeah, which one?
Number 13.
Okay. Oh, yeah, this one was a little cheap. So this says largest acute angle. If you missed it, I'm betting it was because of that. So at which point on the planet's orbit do the vectors representing the planet's velocity and the vector representing the sun's gravitational pull make the largest acute angle? So if I draw all these vectors, on the top here, they're all going to be obtuse. I'll just draw them anyway, though. So here's the velocity vector, and this would be the gravitational vector, and here this is gravity, and this is velocity. So those are both obtuse. On this side, gravity is going to pull right toward the sun, and the velocity is tangent. So there's an acute angle. And then here velocity is this way. Gravitational pull is like that. So this is acute, but it's a little smaller. Here I've got gravity this way. And I'm not making the length of these proportional. I'm just trying to get the angle right. And then there's velocity, which is tangent. So this is even smaller. And this looks like it's maybe growing a little bit. But of all these, this one's almost 90 degrees. If that's gravity and this is velocity, so these 1, 2, 3, 4, these are all acute. This is the largest acute angle. So it'd be near letter C. The acute angles are everywhere from here through the bottom part. And when these angles are acute, gravity is generally pulling in the same direction as velocity, speeding everything up. So in the part of the ellipse where we're speeding up, all the angles are going to be acute. At these two ends, this is where the angles are 90 degrees. So really we're just looking for the place on the bottom half of this ellipse closest to one of the two ends. Other questions?
Can you do 8 and 9 on multiple choice?
Yeah. So 8 is take a formula and do some manipulation with it and figure out well, let me just write it and then talk about this kind of question. So gravitational force you can do as mg, but here we're talking about two masses separated by a distance r. So this is really the formula that's in question. I'll call it mass 1, mass 2 over r squared. So Mr. Pennington started these multiple choice questions, and they really just test your ability to say, this force, is this directly proportional to big G? Is it inversely proportional? Is it proportional to the square of this thing? It's kind of teasing out how the relationship between the different parts. So this just said, it tells us the gravitational force when they're separated by a distance r. That's 400. If the distance between the two masses is cut in half, what's the new force going to be? So I think the best way to do this is to start with the equation for force. And then let's say this is representing the new force. And all I'm going to do is, instead of r, I'm going to put in half of r. So this, and then I'm going to see how the new force and the old force compare. And then I'll go from there. So G, M1, M2. If instead of r, I put in r over 2, this becomes r over 2 squared. So this is going to be G, M1, M2 over r squared over 4. And I don't know how math savvy you are, but basically one way to look at this is I'm dividing by a fraction. So I can multiply M1, M2 by the reciprocal of this. So this is just going to be G times M1, M2 over r squared times 4, basically. So this is the force I had to begin with, and this is the new force I'm going to have. It's just going to be whatever I began with times 4. So if I started out with 400, 4 times that is 1600. That's one way to do it. Usually there's a really concrete kind of way to do it, and I think you could do that by just substituting in numbers. So if I just made this 400 to begin with, I don't know. That's kind of an onerous way to solve this problem. I could come up with some numbers that equal 400 and then see what happens if I double that one, but no, I don't think that's easier in this case. David, did that make sense?
Yeah. Are you gonna give us like more room on multiple choice to like show our work?
No, but you can have scrap paper. Anytime you want,
Okay.
just pull out some extra paper and staple it on your test when you're done.
Okay,
Otherwise,
cool.
some people won't need it, and then I'll just be using more paper for sure rather than maybe. Other questions? Yes, Maddie. Oh wait, yeah, I will. But David asked about number 9, so let me do that one, and then I'll do number 4. Number 9, I'll read it, and then I'll explain where it's going. So it says the table below represents 4 planets whose masses and radii are expressed in terms of Earth's mass, Earth's radius, different masses dropped from a height of 10 meters, neglecting air resistance, in which case will the ball fall faster. So this boils down to on which planet do things fall faster. On the Earth, things fall near the surface. They fall at about 9.8 meters per second squared. So that 9.8 meters per second squared, if it's 4 meters per second squared on another planet, it's not going to fall as fast. It's 20 meters per second squared, it's going to fall faster. So really, if I can figure out what G is for all these planets, or at least how their G's compare, then I'll be able to do it. And we've got a formula for that, or at least one you can derive. G equals the gravitational constant times the mass of a planet over r squared. So it's proportional to the mass of the planet over r squared. So if the mass of the planet goes up, G goes up. If the radius of the planet goes up, G goes down. So what you can do, you can leave this in or leave this out, but really calculate this for all these different options. So for option A, if I just say that the G is proportional to, I'll leave the big G in there, 1 Earth mass over 1 squared. Notice that ball mass, totally unrelated to this. This is the mass of the planet. Doesn't matter how much mass things have on a planet. That's not going to affect how fast they fall. So all that's irrelevant. So if I do this, I get 1 over 1, which is just G. And if I do this for choice B, I get the mass of the planet, which is 4, divided by 2 squared. Sounds like I've got cicadas in my computer, which would be 4 over 4, which is, again, G. If I do this for C, I get 5. G times 5 over 1 squared, which is 5G. So that's going to be bigger than these other two. But the last one, that's going to be the biggest because I'm multiplying by 2 times the mass of the Earth, and I'm dividing by, this small radius really makes a difference, 0.5 squared. So it's going to be 2 over 0.25, which equals 8. So that's the biggest. All right, Maddie, which one? You said number 4?
Yeah, no problem.
Okay. So David, did that make sense? Okay.
Yeah, that makes sense.
Do you people at home hear the
Thank you.
cicadas in my computer? No? Oh, good. Okay, So yeah, number 4. This one, I think this was probably the trickiest. This whole idea of the scale suggesting that her weight is 3 times the normal value. That's kind of tricky. So somebody's standing on a scale, going around and around and around on this ring of fire ride, except usually you don't just stand free on a scale like that. 11 meters per second is the speed, and her weight is 3 times the normal value. So the weight on a scale, anytime you're standing on a scale, the reading on that tells you how hard the scale's pushing against you, which is another word for normal force. So the forces that are acting on her, she's got 2. The scale's pushing her up, and her weight is pushing her down, or pulling down. So those are the only 2 forces. There's no air resistance or anything else here. Because this is a circle, a uniform circle, then I know that the net force acting on her is mv squared over r. And because she's at the bottom, I know that that has to be positive, because the net force, if you're in a circle, is always toward the center. If the center's above you, then the net force is going to be up. So that's how I got this. So that's one way to get the net force. The other is to add the individual forces. The scale's pushing her up, that's the normal force, and then her weight is pulling her down, that's the other. So that's where the Fn minus mg comes from. So really it's just the case of setting these equal to one another and solving with one twist. So I've got mv squared over r equals normal force minus mg, but this is crucial. The scale says her weight is 3 times the normal value. So normally her weight would be mg, right? And the scale is reading 3 times that much. So that means the normal force is 3 times her weight. So I can just plug in 3 mg for the normal force. And there may be other ways to do it, but that's what I did. So if I put 3 mg in here, one thing I could do, I could say 3 mg minus 1 mg equals 2 mg. And then I could divide both sides by m, but I think I just wrote it all out, divided everything by m, and then I subtracted 3g minus g is 2g. So then I get this. And then I just plugged stuff in and did some more algebra. Cross multiplied. But that was the tricky part. Substituting 3 mg for the normal force. You can't get it unless you do that.
Yeah, that's what I missed.
Right. So if you had done that on the test, I probably would have just taken, this would be, if this was a 4-point question, I would have taken off 1.
Okay.
Yeah. No, you don't need it at all. You could do it with that. So if I hadn't canceled out all the m's, I could have put 60 in there, but it wouldn't have made a difference. Other questions? Let me show you the other thing. This is the thing that Jackson pointed out that at first was wrong. So if anybody was really getting ahead on this, you would have noticed it. Originally on my answer key, I had a 1 down here instead of 4.2. If you noticed that at some point, I fixed it, but hopefully nobody else was tripped up by it. Yeah, Thomas.
Can you explain number 11?
Sure. Yeah, the other class asked about this, and I gave them a really long-winded answer. So let me give you the short answer first. So I'll draw a picture, but then I'm going to keep it short. But then I might give you the longer answer. I don't know. We'll see. See what it feels like. So this is out in space, and to make it look like it's out in space, I'm going to have the person standing there, and the space station's orbiting around. So this is like the 2001 Space Odyssey thing. So it's simulating the field of gravity. So the short answer to this is gravity on Earth is we experience that as it's kind of like it's a force that would accelerate us at 9.8 meters per second squared. You know, if the floor were pulled out from under us, we would accelerate at 9.8 meters per second squared. And so the quick way of doing this is just to say this is really the acceleration of gravity. And out here I don't have gravity, but I can simulate it with centripetal force, which is v squared over, or sorry, centripetal acceleration, v squared over r. So if I just set v squared over r equal to 9.8, I can get the answer from that. So in this case, these are the same numbers from the warm-up today. R is 5 meters. So 5 times 9.8 is 49. 49, what would the units be? Seconds squared? No. Wait, if I multiply meters by meters per second squared, it should be over seconds squared. What am I doing here? I'm getting hung up on the units. Oh, this is going to be meters squared per second squared. There we go. Equals v squared. So take the square root of both sides and you get v equals 7 meters per second. Now, a little bit of a longer answer, which I do think is really important, is I probably should have done this as a warm-up, but how do you feel like right now? Can you tell there's gravity when you're sitting still? If suddenly the floor were pulled out from under you and your desk were pulled out from under you, would you feel any different? Would you feel that? Yes. So you are feeling gravity right now. Because if it went away, just if the floor dropped out, you would feel a change. So what's the sensation that you feel right now? This is going to be you. I'm just drawing somebody with some hefty guts. This is you sitting in your chair. Maybe you've got your hands rested on the table. So what part of you feels gravity right now? What part of you would feel very different if your chair and the floor just suddenly disappeared? Your stomach, yes. So, and specifically, this is your small intestine and your colon and whatnot. So right now, all that is doing what? Yeah, it's sort of squashed down. It's smashed down against the bottom of your abdominal cavity. And if suddenly the chair disappeared and the floor disappeared and you started to fall, this would be like the little, let's just imagine there are little people in there too. The little people would be falling and your guts would be falling and you'd be falling and you would all fall together and they could just sort of hover around in there and play and turn flips and things because they would no longer be being pressed against the floor. So you feel, so whenever you just suddenly free fall, that's this basically the normal force of the bottom of your abdominal cavity pushing up against your guts and the normal force of the guts that are piled on top of those pushing against them. All those forces go away and it just feels really weird. And the normal force of your chair pushing against your butt and your butt pushing against the chair, that goes away too. So this is all really about, it's all normal forces. Right now, I feel my chair pushing against me. That's the main thing I feel. And if that was gone, I would notice. So if you want to simulate gravity, really what you need to do is you need to simulate a normal force. You don't have to do it this way. If you somehow had the capabilities, you could have somebody standing out in space, not doing anything, and you could just put a rocket right here. I know you don't really need fins on rockets out in space, but here's a rocket, and suddenly you ignite this and you start to shoot the scale that way. They'd feel, and as long as you were accelerating 9.8 meters per second squared, pushing the scale against them the whole time, they'd feel just like they were standing on the ground. So what you're really trying to do is get a normal force that's equal to the it's the same thing as the centripetal force, and you want that to equal your weight on Earth. So if I write the centripetal force is the normal force, and I want that centripetal force to equal my weight on Earth. I can cancel out these m's, and I get G equals V squared over R, which is basically what I did before. 9.8 equals V squared over R. Any other questions? You've had enough, huh? People at home, do you have any other questions? These people have had enough. I'm really glad I deleted the homework assignment. So if there's no homework, but I have a sneaking suspicion that a lot of people haven't actually been through these, you should definitely do the problems. I would even recommend, if you missed one, printing this out again and trying to do it with no help. And that's, no, there's no video of this. Would you like me to make one if I have some extra time? All right, there is one for the previous practice test, for the 2018-19 test, but there isn't one for this. If I do one for this, I'll send you an email. All right.